So, yesterday we talked about, we derived the space phasor based voltage equations for the stator and rotor with respect to alpha beta reference axis, and alpha beta what we call the alpha is placed along the A phase reference axis. So, alpha beta we call the stationary reference frame. Now, what finally what we want the instantaneous position of the flux. So, we want a general rotating reference frame dq such that D should be always placed along the psi r axis. So, while doing so, the current IS, stator space phasor current, we can split along phi r and orthogonal to it, and by controlling the orthogonal component we can control the torque, same like in a separately excited DC machine, and by controlling the keeping the current along the psi r constant under all dynamic conditions, then flux will be kept constant. So, we will get a performance similar to a separately excited DC machine. So, what we want require here, instantaneous position of the psi r is needed. Okay. So, now let us derive the stationary reference frame model alpha beta. Let us derive it with respect to a general rotating reference frame dq. So, that then we can appropriately place the speed of the dq, so that we can get either alpha omega, that the speed of the reference frame is 0, then again we will get alpha beta, speed of the reference frame is equal to omega s, we will get the synchronous reference frame, omega speed of the reference frame is equal to omega r, we will get the rotor reference frame. So, what we are going to do now is a general dynamic equation with respect to a general rotating reference frame. So, let us go to the next page. Let us again draw our axis. This is the alpha and this is beta. Okay. So, we already got the voltage space vector space phasor based stator equation, and the rotor equation. This is IS, then we said this is the rotor A axis or rotor alpha axis, rotor A axis. I will make it bigger so that it be clear. Rotor A axis. Okay. So, here with respect to rotor axis you have the current IR, this is theta. So, equations we are derived. We will again write the equation alpha beta with reference to alpha beta. We will repeat the equation. Vs is Rs Is plus Lss d by dt Is plus m into d by dt of IR, originally defined with respect to the rotor axis, that is IR into e raised to j theta. We want to bring it to the stator axis. So, this IR space vector we have to multiply it by e raised to j epsilon. So, angle is increased now. This is our epsilon. Okay. So, stator equation defined with respect to alpha beta axis. Now, the rotor equation also we want to define with respect to alpha beta axis. So, that is RR IR e raised to j epsilon multiplying by e raised to epsilon, we will be defining with respect to alpha axis. That means, from the rotor axis we are coming to the alpha axis. plus LRR d by dt IR e raised to j epsilon plus m into d by dt IS e raised to minus j epsilon. This is the starter current. This starter current IS underscore starter space vector defined with respect to the starter by multiplying e raised minus, it has gone to the rotor axis. So you will get the current starter current, the component of the starter current which is contributing to the induced voltage in the rotor multiplied by m into d by dt. So this is defined with respect to rotor axis. Now everything we have to define with respect to starter axis, so it will be e raised to j epsilon. This e raised to j epsilon is to bring to the original rotor voltage equations defined with respect to the rotor axis should be brought to the starter axis. Now what we want? We want to bring everything to a general rotating reference frame. So let us see the general rotating reference frame. We are not worried about the psi r now. This is D and perpendicular to that one is Q. This is the DQ axis. And we know instantaneous position of the DQ with respect to the starter axis, the angle position is rho. So now DQ axis, general rotating reference frame. Okay. Now let us transfer the starter equation to the general rotating. Vs originally defined with the starter axis, we have to move to the D. Now the angle, you are going, this is the general rotation. Anti-clockwise rotation is the general rotation of all the axes. So when we go here, angle is, we have to reduce it. So e raised to minus j rho plus Rs is square underscore e raised to minus j rho plus LSS. Now this dis by dt, this is the complete voltage term. This voltage term we want to bring it to the dq axis. So this will be outside the d by dt term. Similarly for the mutual inductance term also, m into d by dt IR e raised to minus j epsilon whole thing multiplied by e raised to minus j rho. The full starter equation we are transferred to the dq axis. Now let us see the rotor. 0 squirrel cage motor. So then RR IR e raised to j epsilon j into epsilon minus rho. This we can do it. We are multiplying by e raised to minus j rho plus LRR d by dt of IR e raised to j epsilon minus rho. Okay. plus m into d by dt of is e raised to j minus epsilon into e raised to j epsilon minus rho. So, all the rotor equation also we have transferred to the PQ axis. So, our dynamic equation is complete. Now, we have to take the real and imaginary component. If you take the, how do you take the real and imaginary component here? See, let us go to the next page. Let us draw our again for clarity our alpha beta axis, and this is, here is our dq, general rotating axis. Okay. Suppose Vs is here. The Vs component along D and perpendicular to Q, this is called VSQ and this is VSD. Now, the same Vs, if you project it to the alpha beta axis, the real and imaginary component magnitude will vary. This is V beta because it is parallel to beta axis, this is V alpha. So, the real and imaginary components are the projection of the voltage space phasor, the projection to the corresponding reference frame axis. Then D gives the real and the Q axis gives the imaginary component. So, if you see here, this is rho. This is rho. This is gamma 1. Okay. So, what is VSD? If we know the alpha beta component, how do you find out the VSD and VSQ? VSD is equal to Vs mod cos of gamma 1 minus rho. What is gamma 1 minus rho? That is this angle. This angle is the gamma 1 minus rho angle. And VSQ is equal to Vs mod sin gamma 1 minus rho. This is true with Is also. Is, the angle is gamma. So, ISD is equal to Is underscore mod cos gamma minus rho. ISQ is equal to Is underscore sin gamma minus rho. What will be for the rotor? So, rotor again, for clarity I will again draw it here. This is alpha beta, this is our rotor axis, rotor A phase axis or rotor alpha axis, rotor A. This is making with respect to this one, this is epsilon, and here is your IR, and this is theta, and our dq will be, okay, dq somewhere here. D, we only know the dq angle, this is q, dq angle is rho. So, here IRD is equal to IR mod magnitude into cos of originally defined with rotor reference phase axis, we have to shift to alpha axis, epsilon, then you have to bring it to the dq. Then IRQ is also equal to IR mod sine of Now let us, our original equation, let us bring to the dq axis. So let us take our starter equation first. Original starter equation dq. Stator equation. That is Vs underscore e raised to minus j rho plus Rs Is e raised to minus j rho plus LSS d by dt Is e raised to minus j rho plus m into d by dt IR defined with respect to the rotor axis, transferred to the stator, and then finally to the dq. Okay. Sorry, this is equal to, not the plus here. Now this we know it. Vs e raised to minus j rho is equal to Vs mod into e raised to j gamma 1 minus rho is equal to Vsd plus j Vsq. So this term is over. Now the second term, that is Rs into Is e raised to minus j rho, that is Rs into Is mod e raised to j gamma minus rho, that is equal to Rs into Isd plus j Isq. From the previous. Now let us see this term. This term, if you see here, this e raised to minus j rho is not inside, it is outside. It is not, see, if it had been inside, then the whole thing d by dt of Isd plus j Isq we could have written. But how to bring the Isd plus j Isq? Let us take it. Let us take the term. That is LSS e raised to minus j rho d by dt of Is. This term. This is the term we want. So what I will do, I will put this e raised to minus j rho also inside. So that will be equal to, that means we are going to find out LSS d by dt of Is e raised to minus j rho. This will be equal to LSS e raised to minus j rho into d by dt of Is. Now the magnitude also we are going to differentiate. So we are taking all the dynamic conditions. Then what is d rho by dt is omega rho. So this will be equal to minus j omega rho into LSS into Is e raised to minus j rho. Okay. So, if you see this equation we can write as LSS into d by dt of ISD plus JISQ, and this is the term what we want. This is exactly this one. So, what about this term? So, this will be equal to, we will bring this one this side. So, that means plus j omega rho LSS, this is again equal to ISD plus JISQ. So, the second voltage term also we solved here, we have solved it. Now, let us find out the rotor term. Same way we will bring the minus j rho inside and then differentiate and separate this term. The same technique we can use throughout. See, in the original equation Vs e raised to minus j rho, this IR e raised to j epsilon, because IR originally defined with respect to the rotor axis, we have to bring to the stator axis. So, it is not minus j epsilon, this is plus, and we are going to the dq axis, that is why e raised to minus j rho. Now, let us take in the stator equation the mutual inductance term, the voltage due to the mutual inductance, that is m into e raised to minus j rho d by dt of IR e raised to minus j epsilon. But we know that IR, this is plus, because we are trying to bring it to the rotor side. IR e raised to j epsilon minus rho is equal to IRD plus JIRQ. See here, this IR originally defined with respect to the rotor axis, when multiplying by e raised to j epsilon, it will come to the rotor stator axis. Then again multiplying by e raised to minus j rho, it will go to the dq axis. So, the real component will be IRD plus JIRQ. But if you see here, e raised to minus j rho is outside. So, we will bring this way here now, m into d by dt of IR e raised to j epsilon into e raised to minus j rho together here. So, this when we differentiate, it will be, first let us take, this will be equal to, first we will differentiate with this term. So, e raised to minus j rho m into d by dt of IR d by dt of IR e raised to j epsilon. Then we will differentiate with respect to this one, that is minus j omega rho m into IR e raised to j epsilon minus rho. Okay. So, here what we want is this term, that is this term, but we know this term is equal to m into d by dt of IRD plus j IRQ. Now, this term will be, this will bring it here. So, this will be equal to plus j omega rho into IRD plus j IRQ. So, this also we split into IRD component along IRD along the D and Q axis. The same thing we can do for the rotor axis also. Let us go to the rotor equation. Now the rotor equation. The original rotor equation is rotor applied voltage is equal to 0 is equal to RR IR e raised to j epsilon minus rho plus LRR e raised to j epsilon minus rho. This epsilon minus rho will transfer all the rotor voltage and current equation defined with respect to the rotor axis. It will be transferred to the dq axis. d by dt of IR e raised to minus j epsilon. See, the rotor equation is originally defined with rotor axis. By multiplying by e raised to minus j epsilon, we are trying to bring it to the stator axis. So, but already we have multiplied e raised to j epsilon minus rho. So, this will be IR mod e raised to j theta. Sorry, this is originally defined with respect to the rotor voltage equation, because due to the rate of change of current of the rotor current, which is defined with respect to the rotor axis, that is IR. Then plus m into e raised to j epsilon minus rho into d by dt of IS, originally defined with respect to the stator axis, now will be defined with respect to rotor axis. Okay. So, this is with respect to rotor axis, this is also with respect to rotor axis. So, multiplying by e raised to j epsilon minus rho will go to the alpha beta axis, and then again from minus rho it will go to the dq axis. So, this dq rotor equation is defined with respect to the dq axis. We know this one, first equation, RR IR e raised to j epsilon minus rho is equal to RR IRD plus j IRQ. Okay, this is RR. Now, let us take this time, second time, that is LRR e raised to j epsilon minus rho into d by dt IR. See, this IR is originally defined with respect to the rotor axis. Now, both the stator and the rotor axis we defined with respect to the stator alpha beta axis. That is why we have multiplied outside by e raised to j epsilon. Now, the whole equation we are transferring to the general rotating reference frame. That is why we are multiplying by e raised to j minus 0. Now, again this we will write as this, we will inside we will bring it and then differentiate, that is LRR d by dt of IR e raised to j epsilon minus rho. This we can write as this is equal to, first we differentiate with the IR, the space vector. So, e raised to j epsilon minus rho into LRR into d by dt IR, then plus j epsilon minus rho, that will be equal to j into omega r rotor speed. D sigma by dt is equal to d epsilon by dt is equal to omega r. So, d epsilon by dt, that is omega r minus omega rho into LRR into IR e raised to j epsilon minus rho. So, if you see here, this equation, when you bring it inside, this we can write as LRR into IR, LRR, oh sorry, d by dt into IRD plus JIRQ. Okay. So, this term will be, this is the one we want, that is this term, is by bringing this one this side, this will be equal to, finally that term will be equal to LRR d by dt of IRD plus JIRQ when this bring here, this will be, we can write plus j into now omega rho minus omega r into LRR into IRD plus j IRQ. So, now let us take the mutual inductance term in the rotor equation, that is this term. Okay, let us go to the next page. M into e raised to j epsilon minus rho into d by dt is originally defined with respect to the stator axis. Now, the component of this one along the rotor axis will be equal to e raised to minus j epsilon. So, this is the voltage term m into d by dt is e raised to j, e raised minus j epsilon. This is the voltage term induced in the rotor. Okay. Now, this one we want to transfer to the stator axis. So, that is why we have multiplied by e raised to j epsilon, and then again multiplying by e raised to minus j rho, we are bringing to the dq axis. So, here also we know is e raised to j e raised to minus j rho is equal to ISD plus JISQ. M into d by dt of is e raised to minus j epsilon into e raised to j epsilon minus rho. This will be equal to first we will differentiate with the first time, that is equal to m into e raised to j epsilon minus rho m into d by dt is e raised to minus j epsilon, then we will differentiate with respect to this one, that will be equal to omega r minus omega rho j into m into is e raised to minus j epsilon into e raised to j epsilon minus rho. Okay. This term we know it is equal to m into d by dt of ISD plus J ISQ. Because these two cancel. Here also these two cancel. So this term is by bringing this one here. So this will be equal to J omega rho minus omega r into M into ISD plus J ISQ. So all the terms we are, all the voltage terms we have brought into the real and imaginary components. We have to separate out the real and imaginary component. Then we will get the real and dynamic equations in DQ reference frame, the real and imaginary component for the stator and rotor. So let us do that one. So the final equation, when we transfer to the real and imaginary component, the stator will be final equation. VSD is equal to RS ISD plus LSS d by dt ISD, then minus LSS omega rho ISQ. So real component, the J component we will put it to the that is the VSQ component we are separating out, D component and Q component, plus M into d by dt of IRD minus M into omega rho into IRQ. Omega rho into omega rho is the subscript here. Sorry, this is the subscript. D rho by dt. D rho by dt is the omega rho. Omega rho. Now VSQ. RS ISQ plus LSS d by dt of ISQ plus LSS omega rho into ISD plus M into d by dt of IRQ plus M omega rho IRD. Stator dynamic equation is ready. Then rotor. Rotor VRD is equal to 0. We are not applying any voltage. So this will be equal to RR IRD plus LRR d by dt of IRD minus LRR into omega rho minus omega r into IRQ plus M into d by dt of ISD, then minus M into omega rho minus omega r into ISQ. Now the Q axis, again 0 is equal to RR IRQ plus LRR d by dt IRQ plus LRR into omega rho minus omega r is the rotor speed into IRD plus M into d by dt of ISQ plus M into omega rho minus omega r into ISD. So we got the dynamic equation in DQ reference frame. Now DQ reference frame, we said the DQ reference frame is rotating with a general speed omega rho. If it is not rotating, that omega rho is equal to 0. Then the equations are defined with respect to the original alpha beta axis. So making omega r is equal to 0. Then everything is in alpha beta axis. The D component become VSD component Vs alpha and VSQ component become Vs beta. Now omega rho is equal to omega s. then we will get the synchronous reference frame. That means our DQ reference frame is rotating with respect to the synchronous rotating reference frame. Okay, that speed of rotation is omega s. Now what we want to align the DQ with the synchronous which is rotating with synchronous speed to the our phi r axis, phi r space vector axis, and phi r is also rotating with synchronous speed. This we will study in the next class.